Let's have a look at this word problem. It states here, a steel section of the Alaskan pipeline had a length of 65 meters and a temperature of 18 degrees Celsius when it was installed. Now looking at this, 18 degrees Celsius tells me that in Alaska, this is probably the summertime. And that would be a good time to install a pipeline in the summertime, rather than doing it in the wintertime when it can get as cold as minus 45 or even lower. So let's look at the rest of this. It says here, what is the change in length when the temperature drops to a frigid minus 45 degrees Celsius? All materials have a tendency to expand and contract based on temperature. I'll write that down here. All materials will expand or contract depending on temperature. General rule is, as the temperature rises, materials have a tendency to expand. As the temperature cools down, they have a tendency to contract. Here we have a couple of pictures of expansion joints, because this expansion and contraction is designed into our economy. And here is a bridge. And this bridge has expansion joints right here. And this bridge, over the summer, winter, it's going to expand and contract, and that expansion and contraction is taken care of by this joint right here. As far as pipelines go, the same thing here. The pipelines will expand and contract depending on the temperature. And this is one design for an expansion joint for a pipeline. There are others. And on a bridge, when you're traveling over a bridge and you feel the car going ka-clunk, 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 it's going over these expansion joints. Let's carry on with the word problem. So we have a pipeline and a segment of the pipeline, and it's 65 meters long. Let's draw that. Here's a segment that happens to be 65 meters long. And there. And the temperature when it's being installed is given to us here as 18 degrees Celsius. And the question is, what happens to its length when the temperature drops down to minus 45? Well, based on what I said up here, we expect this length here to shrink. It's going to contract. So I'll draw another sketch of this same pipeline. I'll go to about here. Because we expect the pipeline to contract because the temperature is going down. And this is going to be at minus 45 degrees Celsius. And this segment here, the amount that it has contracted, I'm going to give this a name. I'm going to call it delta L. This length from here to here, call that the change in length. And this delta L, well, that's the Greek letter delta. And sometimes I just simply say change in length. Change in, this delta represents change in something. Change in length, change in volume, change in something. That's what the delta represents. And it's a subtraction. And I'll show you that in a few moments. So it's going to shrink this much. What is the final length then? Right here. So that final length, we can put a short equation to this, is going to be the original 65 meters plus this change right here, this change right here, delta L, plus, and I'm going to put this in brackets, delta L. And that doesn't quite look right, does it? It says 65, and I'm going to add this piece when I really should be subtracting it. If I'm starting with 65 millimeters, then this length here should be that 65 minus this little bit. But this is correct, and we'll see why this is correct near the end of this word problem. I'm going to do this again, going the other way. And this is just an addition to the word problem itself. So let's not draw this pipeline again. Here it is. It's 65 meters long. And this time, let's say this is in somewhere in the desert. It's starting at being installed at 18 degrees Celsius. And we'll imagine this being somewhere out in the Nevada desert, somewhere hot. And the temperature is going to go to, instead of minus 45, it's going to go to a plus 45. And that pipe is going to expand. Plus 45 degrees Celsius. It's going to get longer. And this segment here that it has expanded, that portion right there, that too is delta L. And the entire length from here to here, that entire length, you can put a simple equation to it, is the original length plus that extra bit that it has expanded. So these two effectively look the same. 65 plus delta L, and 65 meters plus delta L. Well, let's carry on with solving this problem right here. The equation we're going to use is in our equation sheet. Which I know I have here on my desk. Here we go. I'm going to use equation 28. Delta L is alpha Li delta T. Change in length is equal to alpha Li delta T. Let's look at that. Delta L is the change in length. That's what we want to find right here. It says here what is the change in length. So we want to find change in length is equal to alpha is the coefficient of linear expansion. It has a comment up here, coefficient of linear expansion alpha. That's this alpha here. Times the original length. This is the initial length, or original length, times delta T. That was our equation. And there's this change in something, as I said here, change in something. This is what is change in temperature. And when we see change in temperature, what this really means is there's a subtraction happening in here. And this is just being truncated down to delta T. So I'm going to expand this out. So the equation looks like this. Change in length is equal to coefficient of linear expansion alpha, the initial length, and this is actually temperature final minus temperature initial. And we'll put down final here. It's a subtraction. When you do this subtraction, you can write it as delta T, or we can expand it, and this becomes a working equation. And it's temperature final minus temperature initial in this order. Now let's look at alpha. Where does alpha come from? The coefficient of linear expansion. Well, this comes from a chart. All materials have their own coefficients of linear expansion. Let's take a look. Here is the chart. Coefficient of thermal expansion. We're talking we need the linear expansion alpha. And here's a list of items. Take the pen out. There's all the various materials, and that is how much they expand. And it needs, well, before I go that, look at the exponents here. They're all 10 to the minus 6. And there's some number in front of it, coefficients. Let's look at that for a minute. For putting something into proper scientific notation, let's say I have a number, 652. I want to put that into scientific notation. The way that's done is you take the first number, put in a decimal place, and then you put in all the numbers afterwards, 6.52 times 10 to the power of 1, 2. So put something in the scientific notation. It's the first digit, then a decimal place, and then all necessary digits afterwards. This will be proper scientific notation. And if we look here, you'll note that they're not using 2.3 times 10 something or 1.9. It's 23 and 19, 17. So they're taking some liberties. And we're interested in steel. Here's steel. And it has 12 times 10 to the minus 6. And that 12 times 10 to the minus 6 can also be written. 1.2 times 10 to the power of, it's minus 6. I have to go down 1 into the minus 5. And the reason this is written this way is such that all of the exponents are the same, all to 10 to the minus 6. Therefore, at a glance, we can look at the coefficients here, and we can see that silver has a larger, greater degree of expansion than, say, glass. 19 versus 3.3. Now I don't have to really worry about the coefficients. And I can see that 29 is greater than 17 and 17 is greater than 12 at a glance. Let's have another look at another text here. And here is alpha, coefficient of linear expansion yet again. Same materials, and here are the values. And you'll note here it's all 10 to the minus 5. And here's the one I'm interested in, steel, 1.2, 10 to the minus 5. And again, they did the same thing here. This author did the same thing, put everything to the 10 minus 5. And it took some liberties with the exponents. Notice this is 0.09. And here is a 0.04. And they do this in order to keep all of these the same, such that at a glance you can see which one has a higher expansion, which one is least. Having said that, when we look at the top, let's stay with this one for a minute. And we look at the units up here. Now these units can either be in per Kelvin or per Celsius degree, based on this chart. Let's go back to the other chart. And we want to know the units. And this is the chart that I'm going to be using to solve our problem. And the unit given to us here is Celsius degree to the minus 1. Going back to our page. Coefficient of linear expansion, 12 times 10 to the minus 6 per Celsius degree. Now what is this Celsius degree? Take here, I'm going to subtract two temperatures. Let's say for the sake of argument, I'm going to take 25 degrees Celsius minus 20 degrees Celsius. Okay. That is equal to 25 minus 20 is 5. And because I've done this subtraction, and in order to know that this is a subtraction, not a temperature, is 5 Celsius degree. When we subtract two temperatures in degrees Celsius, the final answer is 5 Celsius degree. This is not a temperature. It is a subtraction between two numbers. So looking at our equation now and putting in the units, change in length is equal to alpha. Alpha, we'll put in some numbers as well. 12 times 10 to the minus 6 per Celsius degree. And the initial length, the original length was given to us as 65 meters. And the two temperature changes. And we're going to go 18 degrees Celsius down to minus 45 degrees Celsius. So the final temperature we're going to go to is minus 45. Minus, and this minus sign, that belongs to the equation. So right here, that's this minus sign and this minus sign, they stay together. It belongs to the equation. So it's minus 45. That's the actual temperature in degrees Celsius. Minus your initial temperature at 18 degrees Celsius. Close that bracket. When I subtract the two, degrees Celsius minus degrees Celsius, the unit is Celsius degree. Therefore, that Celsius degree and this Celsius degree will cancel out, leaving me with just meters. Now the step that I missed here, and I'm just going to go back and do it, is write down what is given. I took liberties and I added an additional step. I skipped this step, so I'm going to go back now and just add it back in. So write down what's given. The temperature initial is 18 degrees Celsius. Temperature final is equal to minus 45 degrees Celsius. Alpha, from looking at the chart or at the top here, we have it as 12 times 10 to the minus 6 per Celsius degree. Celsius degree to the minus 1 means it's in the denominator per Celsius degree. initial length is given to us as 65 meters. And the change in length is what we want to find. Now, knowing all of this, we can put them into the equation as I have done here. Being mindful of this negative sign right here. Wherever the 45 goes, that negative sign goes with it. Hence, minus 45. This negative sign belongs to the equation itself, so it has to be here. And then this one here will be the initial temperature. Having said that, let's go ahead and solve. Change in length is equal to, putting all this in the calculator, it looks something like this. Being careful of this part right here. 12 10 to the minus 6 times 65 meters. And subtracting these two is actually an addition. Minus 45 minus 18 comes to minus 63. And it has no units. The Celsius degrees and Celsius degrees canceled out. All that's left over is the meter. Now putting these numbers in the calculator, the only unit left over is meter, and that's good because length has units of meters. Change in length then is equal to, and this negative sign is going to result in a negative number, minus 0.04914 meters. Note, this minus sign doesn't represent a negative length. There is no such thing as a negative length. No such thing as a negative length. This minus sign here represents a shrinkage. It's going to shrink by that much, a positive value. If you go back to the sketch, here it is. It's starting this long, it's going to shrink that much. And if I measure that distance from here to there, that distance will be 0.049 meters, a positive length. That negative sign represents a shrinkage of positive 0.049 meters. It's there for mathematics. This is here, that negative sign here. You need that for the mathematics. So the answer to the question itself, it says here, what is the change in length? What is the change? We're looking for delta L for that particular pipe. Well, the change in length is equal to a shrinkage, so represent that by the negative sign. And we'll go to significant figures. Let's go to sig figs. And we're going to ignore the temperatures. We'll go with the length. They're all 2 nonetheless. And 12.049 meters. And that negative sign represents a shrinkage. Okay. It is not a negative length. Now let's look at this here and put it into the equation, which we said earlier. So we'll take this a step further. So what is the final length? We'll call it final overall length. And that brings us back to what I wrote up here, 65 plus the delta L. That would be the final overall length after the shrinkage has occurred. Putting those here. Final length is equal to the 65 meters. And I wrote down, as you can see here, plus a delta L. Plus, and the delta L has that negative sign in front of it. As I said, that negative sign is for the math. Minus 0.049 meters. Therefore, final length is approximately 65 minus the 0.049, and we get, let's do this here, 65 minus 0.049, change that, 64,951. So it's going to be less than the original 65 meters, and hence the reason I wrote it like this, 65 plus that delta L, because that delta L can be negative, in which case it'll count for this thing here being a subtraction. In here, the delta L will be a positive value, and then it'll account for the expansion. But the equation is written the same way, 65 plus delta L and 65 plus delta L. And that negative sign is the reason for that. And this final answer, well, it's not to any sig figs. Our answer is this one. And what is 0.049 meters? Let's change to something we understand. 0.049, the shrinkage of 0.049 meters. And let's change that to, let's see, put meters in the, go to centimeters. 1 meter, 100 centimeters. And that's equal to, if we take that, 0.049 times 100, 4.90 approximately, 4.90 centimeters shrinkage over that 65 meter length, which is not a lot. But you take that pipeline over miles, many, many miles, that becomes a significant amount.